Greetings, class. Have you ever wondered how every single element in the universe, from the carbon in your very own DNA to the gold in a ring, gets its unique, unbreakable identity? It all comes down to this hidden, microscopic world of subatomic particles that basically act as the universe's ultimate barcode system. Today, we will study foundations of atomic structure and isotopes.
So, here's our agenda for this explainer. We'll start with proton and nucleon numbers, move into calculating subatomic particles, and then explore isotopes and their properties. After that, we'll look at the applications of radioisotopes, the formation of charged ions, and wrap it all up with some key summary points.
All right, Section 1, Proton and Nucleon Numbers. Let's get into our introduction to the proton number and the nucleon number.
Okay, so every atom contains subatomic particles, right? Protons, neutrons, and electrons. Understanding these particles is absolutely essential for identifying elements. Let's start with the proton number, also known as the atomic number, which is represented by the symbol Z. This simply refers to the number of protons in the nucleus. Every single atom of the same element has exactly the same proton number. It's what literally determines the identity of an element. For instance, hydrogen always has 1 proton, carbon always has 6, oxygen always has 8, and sodium always has 11. It basically acts like an identity card for the element. So, if Z equals 11, it is automatically sodium, no questions asked. And as a quick reminder, the entire periodic table is arranged according to this increasing proton number. I always tell my students, unlike a fake ID at a club, an atom can never fake its proton number. It's just hardwired into its existence.
Here are the core details regarding this topic. Review them intently for they are deemed crucial for your finals.
Next up, we have the nucleon number, or mass number. The symbol A refers to the total number of protons and neutrons inside the nucleus. So the formula is just A equals protons plus neutrons. You see, protons and neutrons contribute significantly to the atom's actual weight. Let's look at aluminum for a second. It contains 13 protons and 14 neutrons. Therefore, A equals 13 plus 14, which gives us 27. So the nucleon number of aluminum is 27. Here's the golden rule you've got to remember for your exams. The proton number identifies the element, while the nucleon number gives you the total particles in the nucleus. While those little electrons are buzzing around on the outside, they have an extremely small mass and don't contribute to this number at all. The heavy lifting is all right there in the center.
Moving right along to Section 2, calculating subatomic particles, we're going to focus on finding the number of neutrons.
Now these calculations, they are guaranteed marks on your AS and A-level exams if you just know the steps. It really is just simple subtraction. The formula is simply neutrons equals A minus Z. So nucleon number minus proton number. Let's take that aluminium example again. With a nucleon number of 27 and a proton number of 13, you just subtract 13 from 27 and boom, you get 14 neutrons. For sodium, it's 23 minus 11, which leaves us with 12 neutrons. It really is that straightforward.
Here are the core details regarding this topic. Review them intently for they are deemed crucial for your finals.
Okay, Section 3, Isotopes and their properties. Let's answer the big question. What exactly are isotopes?
Let's play atomic detective for a minute. If all atoms of a specific element have the exact same number of protons, how is it possible for them to weigh differently? Well, the answer lies in isotopes. Isotopes are atoms of the same element with the same proton number, but different nucleon or mass numbers. I really want you to lock that exact definition into your memory. Their masses differ solely due to varying neutron numbers. So they belong to the same element, they just carry a slightly different load of neutrons in their nucleus.
So why do isotopes behave the way they do? Well, they actually have the exact same chemical properties because they possess the exact same number of electrons, especially those all-important outer shell electrons. This means they react similarly, form the same types of compounds, and show nearly identical chemical behavior across the board. For example, all isotopes of hydrogen will react with oxygen to form water, no exceptions. However, you will see slight differences in their physical properties, things like density, mass, and the rate of diffusion. And these differences occur simply because isotopes contain different numbers of neutrons. It's a great reminder that electrons really dictate the chemistry, while neutrons just change the physical weight.
Now, chemists love a good shortcut, so we use a really efficient visual shorthand for this. The nucleon number, A, is written at the top left of the symbol, while the proton number, Z, is written at the bottom left. So the general form is A on top, Z on bottom, right next to the element symbol X.
Take a boron isotope, for example, which has 5 protons and 11 nucleons. It's written with an 11 on the top left, a 5 on the bottom left, next to a capital B. This is incredibly practical because it instantly hands you both the proton and neutron information without you having to spell the whole thing out.
Let's see how this works with hydrogen. If you look closely, notice how the proton and electron count stays at a constant 1 across the board. But look at the neutrons. They step up. 0 for protium, 1 for deuterium, and 2 for tritium. Deuterium, which is often called heavy hydrogen, is heavily used in scientific research and nuclear reactors. And tritium, with its 2 extra neutrons, is actually radioactive and used in various medical applications. Which perfectly segues into Section 4, Applications of Radioisotopes, focusing on their medical and industrial uses. You know, these atomic properties aren't just dry textbook theories. They have profound real-world impacts on modern technology. In the medical field, radioisotopes are absolutely vital for the treatment of certain cancers, scanning body organs, and checking thyroid gland activity, like using radioactive iodine, for instance. And out in the industrial world, they're used for detecting leaks in oil and gas pipelines, measuring paper thickness in factories, and tracing chemical movement in complex systems. It's pretty amazing how these unstable isotopes actually help stabilize our modern industries.
These are the key points related to this topic. Focus on them carefully as they are considered essential for your exams.
All right, Section 5, Formation of Charged Ions. We are looking closely at protons, neutrons, and electrons in atoms and ions. So far, we've mostly discussed neutral atoms. But what happens when that delicate balance gets disrupted? In a standard neutral atom, your positively charged protons perfectly equal your negatively charged electrons. That means the overall charge is just 0. A magnesium atom, for example, has 12 protons and 12 electrons. But atoms may gain or lose electrons, forming charged particles called ions. And remember, protons never, ever leave the nucleus in standard chemical reactions. This is entirely an electron game. Let's break down exactly how this works by comparing the two scenarios. When an atom gains electrons, we see the formation of negative ions, which are called anions. Take a chlorine atom, starting with 17 protons and 17 electrons. If it gains 1 electron, the result is 17 protons and 18 electrons. It becomes the chloride ion, Cl-, carrying a single negative charge. On the flip side, we have the formation of positive ions or cations. This happens when an atom loses electrons. If a magnesium atom starts with 12 protons and 12 electrons, and it loses 2 electrons, it's left with 12 protons but only 10 electrons. So it becomes Mg2+, with a 2+ charge. Simply put, more electrons means a negative charge, fewer electrons means a positive charge. Let's tie all of this together with a classic A-level worked example. We'll walk through this just like a whiteboard problem. Consider the sulfur-33 ion with a 2- charge. First, we know the proton number is 16 and the nucleon number is 33. To calculate the neutrons, we just subtract 16 from 33, giving us 17 neutrons. Easy enough, right? Now for the electrons. That 2- charge means it gained 2 negative electrons, so we bump our 16 electrons up to 18. So the final result is that the sulfide ion contains 16 protons, 17 neutrons, and 18 electrons. Master this logic, and you're going to absolutely ace these questions on your exams. And finally, Section 6, Key Summary Points. These are the important summary points you need for your examinations. These concepts are heavily tested, so let's do a rapid-fire review. Remember, your proton number, Z, is literally just your number of protons. Your nucleon number, A, is the total of protons plus neutrons. Want to find the neutrons? Just calculate A minus Z. Keep in mind that isotopes have the exact same protons but different neutrons. For a neutral atom, protons perfectly balance the electrons, and when that balance shifts, negative ions are the ones that gained electrons, while positive ions lost them. Take a quick mental snapshot of these rules right now. Before we wrap up this explainer, I want to leave you with something to really think about. If an atom's identity is strictly locked to its proton number, what exactly would happen to our universe if a physical process suddenly began adding extra protons to the nuclei of everyday elements? Just imagine how the very fabric of reality and the entire periodic table would spontaneously rewrite itself. Ponder that until our next class. Keep studying hard, and I'll see you next time.
The screen presents essential keywords for this topic categorized by different exam boards. These terms need careful focus while studying as they are very important and should not be ignored at any cost. Moreover, past paper analysis for each board and paper type is also included. Pay close attention to this section as it will significantly strengthen your preparations. Also make an effort to understand how each keyword is used in the context instead of just memorizing them separately. Regular use of these terms in past paper practice will improve your accuracy and exam performance.
Please subscribe our channel to get more educational videos. Thank you.